Hi guys, my name's Lauren Smith. I'm a 625 point student and I'll be taking you through to 2019's higher level question 6. Today's question is a mechanics question all about satellites, and it's a tricky enough question, so we better get into it. Okay, so here is the first look at our question 6. And up on the top we have a little blurb of information about satellites of all different kinds, including weather satellites, communication satellites, and global positioning satellites. And our first two questions, here and here, are based on this theme. Okay, so before we dive into part 1, I just want to draw your attention to page 56 of the Formula and Tables book, in which we will be looking at, in particular, Newton's law of gravitation, which we will be quoting directly in our answer. In part 1, we're asked to state Newton's law of universal gravitation. Note that they do ask us to state the law. We don't need to describe it or literally anything else. It's just state. So a plain and simple definition will do. Now you can either state the law verbally or mathematically. Either or are acceptable in the marking scheme. Okay, so those of you who would prefer a more verbal definition, the law itself is split into two parts. Each will get you 3 marks each. The first part being that the force is proportional to the product of the masses. That will get you 3 marks. And for your second part, the force is inversely proportional to the square of the distance between them. Another 3 marks. Now, for those of you who are more mathematically inclined like myself, I've given the mathematical description here. On the left, I've given the formula, which is the basis of this law, to the left, and that, just stating that, will get you 3 marks, which is why it would be my biggest tip, even if you preferred the verbal definition, always stick in the formula from the Formula and Tables book, as no matter what you state verbally for the law, you will pick up marks. You are guaranteed those 3 marks. For your next 3 marks, you're of course going to have to notate the formula, which is standard practice in the Leaving Cert. So all of my labels, from the force up here down to the mass of the second body, all describe this formula. Okay, so before I move on to part 2, I'd like to again bring you back to page 56 of the Formula and Tables book. But this time we will be looking at the period of a satellite formula, which again we will be quoting in part in our answer. And we are asked in part 2, what is the relationship between the period t and the radius r of a satellite? Again, like part 1, the verbal or the mathematical description of the relationship is acceptable. The verbal description is as follows. The period squared is directly proportional to the radius of the orbit cubed, and that will get you 3 marks in full. For those of you more mathematically inclined, we're going to give the mathematical description of the relationship. And if you're talking about proportionality and you want to describe it using mathematical notation, you always have to include this symbol here. Again, the period squared is directly proportional to the radius of the orbit cubed. Again, just to be on the safe side, it's not explicit in the marking scheme, but I would do it anyway, just to be on the safe side. Just notate your variables. Make the examiner realize that you know what you're talking about. And this description will get you 3 marks. You can also see this mathematical relationship from the formula we saw in the Formula and Tables book as well, in that we had t squared is equal to 4 pi squared over gm multiplied by r cubed. These two are clearly proportional because we have here one variable and another variable on either side of the equation, and the only thing that they differ is by this constant of proportionality here, because all of these symbols are constants. On to the next section of our question, which is all about the Meteosat 11 weather satellite. And we are told it is in geostationary orbit above the equator. And we're asked a couple of questions on this subject. Okay, so in the third part of our question, we're asked which has a longer wavelength, visible or infrared radiation. And of course, the answer is going to be infrared, and that's going to give you 3 marks for that statement. Now, a little bit of a tip, infrared has the word red in it, and light on the red end of the electromagnetic spectrum tends to have a larger wavelength. Just keep that in mind. On to part 4, we're asked to describe how infrared radiation can be detected in the school laboratory. The description is as follows. Infrared radiation can be detected by its heating effect using a blackened thermometer bulb. Describing that it can be detected by its heating effect will get you 3 marks. And also describing that you use a blackened thermometer bulb will enable you to detect this heating effect will get you 3 marks. Always when you're describing a demonstration or anything like that in your exam, include what you're detecting and how you're detecting it, i.e. what piece of apparatus are you using. In part 5 we were asked, what is the period of the Mediaset 11? And the answer, which will get you 6 marks, is 24 hours. Just stating this is completely fine and will get you your full 6 marks. No need to write large sentences. This will do. And this comes from the fact that it is in geostationary orbit above the surface of the Earth. Now, satellites which are in geostationary orbit have characteristics. The first being that the period of the orbit is 24 hours. The satellite, when it's in this orbit, moves in the same direction as the Earth rotates, and it also orbits in the equatorial plane, i.e. the plane slicing through the equator. Okay, so before we move on to the next part of our question, I just want to draw your attention to a couple of pages in the Foreman Tables book. The first being page 56, where we're going to be looking at the period of a satellite formula. And the next being page 46, where we're going to be looking at the gravitational constant, capital G. And the question asks us to calculate the satellite's height above the surface of the Earth. For this question, we're going to be using the formula for the period of a satellite, which I've just put down right here. By the way, just putting this formula down will automatically get you 3 marks out of a possible 6. The reason why we're going to be using this formula is because, well, we know all the values of the constants like pi and g, and we know the mass of the Earth that's given to us at the end of our question. We also know the period of the satellite because it's in geostationary orbit, therefore the period will be 24 hours. And all we need to find is r. R, however, is not the height above the surface of the Earth. It is the radius of the orbit, and it's measured, as you can see in the diagram I've provided to the left, from the center of one of the bodies to the center of the other body, or the center of mass rather. And this is why I'd always recommend you to draw a diagram, because it can really help you visualize physically what is going on. So in fact, r here is equal to h plus the radius of the Earth, and we are given this at the end of our question. We'll sub it in later, and we need to find this h. Now we know what g is. We saw that in the Foreman Tables book. We know what the mass of the Earth is. That's given to us at the end of the question. And we know what t is. It's 24 hours. However, hours is not an SI unit. And because we're converting between different physical quantities, i.e. we're going from seconds here, we're using kilograms here, and we're going to be converting it into meters here for the radius. We're going to need to put them into SI units, i.e. seconds. So getting up our calculator, we have 24 hours times 60 minutes in an hour times 60 seconds in a minute. It's going to give us 86,400 seconds as our period. So now we can just input everything in to our formula. Now, as you can see here, I've just substituted everything into the formula. I haven't yet put in the radius of the Earth yet, just because there's just going to be a lot of zeros going on, and we can leave that until the very, very end, after we've manipulated this monstrosity here. And here, before I've calculated any values at all, I've again remanipulated it, and I would encourage you to always put all of these workings in the marking scheme. Because as long as you have these down, if you make a mistake with the calculator, it's easier for the examiner to see that it's a mistake with a calculator rather than a mistake or a gap in your understanding of what's going on here. Therefore, they won't be as inclined to take marks off of you. Okay, so we can put this now into the calculator. So setting h plus the radius of the Earth all cubed. We're going to get up our calculator using brackets to multiply out everything. Hitting that equal sign, we get this value here in scientific notation, which I'd encourage you again to put down in your answer sheet. Now let's cube root both sides. And if you see here, I've kept the value up on the calculator. If you press off, shift, we're just going to cube root it. But this will be stored as an answer, so you don't need to type out the whole thing again, saving time, which is what we love. And we're given this value here, which I refuse to call out because there are just too many digits here. Now, the radius of the Earth is equal to 6,400 kilometers, which then, when you put it into SI units, because we're going to look at meters, not kilometers, is 6,400,000 meters. And we're going to sub this in, and we can get the height above the surface of the Earth. Now, h is equal to this minus, because it's stored as an answer, the radius of the Earth, which is 6,400,000 kilometers. Be careful, remember, count the number of zeros. And we're going to get this value here, which in scientific notation is 3.596 times 10 to the power of 7 meters. Don't forget your units here. And that will get you your final 3 marks. Okay, so before we move on to answering the rest of our question, I want to bring us back to the original question, where we're going to be dealing with a new global positioning satellite. We are finished with the previous satellite, that's done, and therefore all the information which we gathered from the first satellite will not matter when we're answering further questions. We are told that this new satellite is not in geostationary orbit, but it does orbit the Earth with a speed of 14,000 kilometers per hour, and that's linear speed. Because it is orbiting the Earth, i.e. the Earth is the second body, we can use constants like the mass of the Earth, the radius of the Earth in our calculations. Okay, so let's get started. So before I get really into anything, I'd like to draw your attention to, again, page 56 of the Formula Tables book. It's becoming a very popular page for this question, where this time we're going to be looking at the acceleration due to gravity formula. However, we're also going to need page 51, but this time we're going to be looking at the centripetal acceleration formula. A is equal to v squared over r. And we are asked to calculate the satellite's radius of orbit, but also its angular velocity. So let's look at part 1, the radius of the orbit. Now, we do know the linear speed, and since they've given us this in the question, that means that we're probably going to have to use it. However, this speed is in kilometers per hour. This is not even close to the SI units we need when we will be using this. We're going to convert it into meters per second. So first, converting it into meters per hour instead of kilometers per hour, multiplying this by 1,000 because that is the conversion. We are given 14 million meters per hour as the new speed. However, we're going to change that per hour into per second, which means that we're going to have to divide 14 million by 60 squared. Why 60 squared? 60 minutes in an hour times 60 seconds in a minute. And this gives us 3,888.88889, but I'm just going to round, giving us an orbital speed of 3,889 meters per second in the nice SI units that we need. And because this is a lot of work in going into SI units, we're given 3 marks for our efforts. Now, the formulas that we're going to be using are the acceleration due to gravity formula and the centripetal acceleration formula. Okay? Why were we going to be using these? Well, we know our constants g and the mass of the Earth. We are looking for r, which is the radius of orbit. We also know v. The only thing we don't know, or we need to find a connection between, is a and g. However, they seem unrelated, but there is one simple fact, that the centripetal acceleration experienced by the satellite is also equal to the acceleration due to gravity experienced by the satellite. So these two are equal, and therefore we can amalgamate these two formulas. However, I must point out that g is not equal to 9.8 meters per second. This is the acceleration due to the gravity if something was on the surface of the Earth. Since this satellite is at a height above the surface of the Earth, as we are told in the question, therefore the acceleration due to gravity is going to be that little bit weaker because it is further away from the center of the Earth. However, no matter, we can still amalgamate these two formulas. And in doing so, in our first step, we get this. However, we do have a common factor in both of these, which is r. So we can multiply across by r, and we can give us a nice expression giving us v squared is equal to g, mass of the Earth, over the radius of the orbit, which we need to find. And this will give us another 3 marks. You are given 3 marks because you have noticed correctly that the centripetal acceleration experienced by the satellite is also equal to the acceleration due to gravity experienced by the satellite. Now, I'm going to rearrange this formula a little bit more. Since our target variable is in fact r, and we know all of these variables on the right, all we need to do is substitute in and calculate our expression for r. Okay, so all we need to do is just substitute these values into our calculator. Now up here on the calculator, we remember I've kept up this value for the linear speed up on the calculator screen, which is great because we don't need to input it further into our calculations ourselves. So we have the product of our two constants on the numerator, and the denominator is just the answer squared, since the linear speed is stored as the answer. Hitting that equal sign, we get our answer for the radius. However, I'm going to be putting it into scientific notation. It's just easier and nicer to look up. Plus the examiner will be impressed. Giving us the radius of the orbit to be 2.65 times 10 to the power of 7 meters. Giving us 3 marks for our final answer. A total of 9 marks for part 1. Now before we move on to part 2, I'd just like to draw your attention again to page 51 of the Form and Tables book, but this time we'll be looking at linear and angular velocity formula. Okay, so moving on to part 2, we need to find the angular velocity, and we're going to be using this formula. V is equal to r omega, because we know the linear speed, we know the radius of the orbit, all we need to find is omega. Just by putting the formula down, you're going to get 3 marks. 3 out of 6, not bad for just copying from the Form and Tables book. I'm just going to rearrange this formula here so we get our target variable on one side and all the other variables which we know on the other. Now just substituting in our values, let's check out the calculator. So we have 3889 over 2.65 times 10 to the power of 7, giving us a very tiny angular velocity, which is equal to, when you round, 1.47 times 10 to the power of minus 4 radians per second. Please don't forget your units, they're very important. You will lose marks if you forget them. But your final answer will get you another 3 marks. So before we move on to our next part of our question, I'd like to draw your attention to page 47 of the Form and Tables book, but this time we're going to be looking at the speed of light in a vacuum constant, which I will be rounding to 3 times 10 to the power of 8 meters per second, which is a perfectly viable approximation to make in the Leaving Cert exam. And we're asked in this next question to calculate the minimum time it takes a signal to travel from the global positioning satellite to the Earth. One of the key concepts here is the word signal. Now, a signal corresponds to an electromagnetic wave, and this signal will have a specific speed. And that speed, which I shall denote as v, is equal to 3 times 10 to the power of 8 meters per second. You might recognize this speed because it is the exact same speed as the speed of light would have in a vacuum. Light as we know it is an electromagnetic wave, therefore, like all electromagnetic waves, it's going to have the same speed as one. So that's an important concept to have. Now, it says here the minimum time. What does it mean by minimum time? Minimum time implies, in this case, minimum distance. Therefore, the minimum distance will be from the satellite to the surface of the Earth. I'm going to denote this distance as s. I'm going to say s for surface, the height above the surface of the Earth. And we remember from our previous parts in our question that this is equal to the radius of the full orbit, i.e. from the satellite to the center of the Earth, minus the radius of the Earth. So the signal travels with this speed across a distance of s, which we know because we know the radius of the orbit as calculated in our previous parts in our question, and we also know the radius of the Earth. So we know this value, which I'm going to calculate here, and just popping this into our calculator, I'm going to get, which I would, even though we're just subtracting the two numbers, I'd put them in brackets because we have this scientific notation here. We just want to make extra sure that the calculator doesn't get confused with what we want, and we're going to get that s is equal to, great, but how do we find the minimum time? We have the displacement, we have the velocity, we can actually find the time due to the velocity displacement time formula. V is equal to s over t. Just stating this formula will get you your first 3 marks out of a total of 6. Even though this formula is not explicitly in the Formula Tables book, you can derive it using the kinematic equations on page 50 if the acceleration a is equal to 0. However, this is a pretty easy formula. You should be able to learn this off by heart. You probably will have to learn it if you are taking higher level maths. I think even in the ordinary level maths course, you'll have to know this formula pretty well. So have it in the back of your mind, and now we can find the minimum time using this concept of minimum distance here. Now I've just kind of rearranged this formula here so that we get the target variable on one side and all of the other variables which we know of on the other side. Here I've substituted it into our formula here, and now we can find the time. Up on the calculator screen, we have the value for this displacement here, and that's going to be stored as an answer. Very handy, we don't need to put it into the calculator at all. And we get a nice neat answer of 0.067 seconds, which of course you're going to have to put down in your answer booklet along with the units, please don't forget them. And then you'll get your final 3 marks. In the last part of our question, we're asked to explain why satellites remain in orbit and do not fall into Earth. And the answer is as follows. Linear speeds are fast enough to defeat Earth's gravitational pull on it. This statement will get you 5 marks. And at a certain high linear speed, when the satellite is at a height above the Earth's surface, no matter how much the Earth is trying to pull it down with its gravity, this linear speed will prevent it from crashing into the Earth and following its trajectory. This linear speed is also tangential to the circular orbit itself.